Okay. Right. Yeah, so that's the title, The Help Inequality on Trees. This is joint work with Malcolm Brown and Matthias Lange, which actually started in this building on the occasion of the workshop, or well, of this program 3 years ago. And okay, help inequality. Well, help is actually an acronym there, and well, HLP, these are the usual suspects. You can also see there in the back, Hardy, Littlewood, Polya. Now, of course, it's not such a great idea to call inequality after Hardy and Littlewood, because you have the problem of uniqueness, and almost every inequality has this distinction. But okay, well, the fact remains that Hardy and Littlewood in 1932 published this equation here, which gives well, a relation between the square integral of the first derivative of a function and the function itself and its second derivative. Right? Now, this is true for all functions for which the right-hand side is finite. Right? So, well, of course, we need to be able to differentiate it at least weakly, and these integrals should exist, and then this inequality holds. Now that this is not entirely a trivial inequality, can already be seen from the fact that equality holds for a rather strange function, which you can see here. So that's the function for which this is equal. Well, of course, it's also equal if you take the zero function, but it's a non-trivial case. Right, and now in 1972, Everett, looking at this equation, asked, well, can't we just replace this second derivative here with a more general Sturm-Liouville operator? So that would be operator of this type, well, 1 over W minus PF dash dash plus QF. The minimal hypothesis, I mean, this should obviously live on some interval as well, and the minimal hypotheses are that P and W should be positive, Q real valued, and we need this local integrability. Then this is a very nice operator, generalization of the one-dimensional Schrödinger operator, for example. And then, well, it is not very hard to guess what the inequality should look like in this case. One would expect something like this, that here we have an associated quadratic form squared, and well, here we have the corresponding weighted L2 norm of f, and here of the operator applied to f. And there should be some constant. And that is, in fact, the form of the help inequality. Now, E is, well, Everett called it the extended Hardy-Wood-Littlewood Polya inequality, but of course E is also the initial of Everett, so in some sense this works out very well. Right, so that's the inequality. Now, of course, this doesn't mean that this inequality actually always holds. Right, this is just the framework, but the question is now, is this actually true, and under what circumstances? What do we need to require of the Sturm-Liouville operator M? Now, this question was in fact answered by Everett, and then later by Evans and Everett, who looked at this. So one can characterize the existence of such an inequality in terms, and also the optimal constant, by the way, k, in terms of the behavior of the M function of the corresponding Sturm-Liouville operator, the Weyl-Titchmarsh M function, which we just heard mentioned in the previous talk. In which way you will see later on. Now, the Evans and Everett in their proof of this inequality showed that studying this inequality has very much to do with looking at the behavior of extensions of symmetric Sturm-Liouville expressions. And well, that in some sense is also not a great surprise if you really think of what functions f we admit here, right? So a usual setup in which such an equation would, such an inequality would exist is, for example, the situation where we have a Sturm-Liouville operator which is regular at one endpoint and singular at the other endpoint, where the so-called strong limit point property. Now, limit point property means that not for all values of the spectral parameter are all solutions in L2. And that can be expressed also in the, if B is the singular endpoint, it can be expressed by saying that Fp dash G bar minus F. So this should tend to 0. And B, that's a Liouville bracket. That's a limit point case. But what we require here is slightly stronger, not just that this difference should go to 0, but that these two should go to 0 individually. And that is termed the strong limit point property. There's a P missing here. Later on, P will be equal to 1. This is why this slipped in. All right, so that should be true at infinity. But then one has this inequality, provided that the condition, which I will mention later, is satisfied. We have this inequality for all elements of the maximal domain. In particular, there is no boundary condition at the point A. Right? Normally, of course, if one has such a Sturm-Liouville operator, one wants to realize it as a self-adjoint operator, and then one would impose boundary conditions. But this is an inequality really about the maximal operator. So there are no boundary conditions. Of course, if you would look at the minimal domain, so for example, if A was also a limit point, singular endpoint, then the minimal operator will be essentially self-adjoint. And then one could simply calculate like this. We take this form, we integrate by parts, then we have these boundary terms, and well, the product here of the operator applied to F with F bar. Now, on the minimal domain, we don't have boundary contributions, so this goes away. And here we just apply Hölder, or Cauchy-Schwarz, and we get this. So we have the inequality with a constant 1. So in some sense, it looks like it's a trivial inequality, but the main point is that we are not talking about the minimal domain, we are talking about a larger domain, so we need to estimate the boundary behavior at A as well. And this is where the constant comes in, and this is why this is an interesting equation. Right, now after seeing that we can replace the second derivative with the Sturm-Liouville operator, you may ask, well, can we not generalize this to more general operators? And the answer is... Pardon?
The function G is very arbitrary.
Ah, that is a Q, sorry. That should be a Q.
Okay.
And these, they are both in the maximal domain. Yeah, this is just a misprint. This should be a Q here. All right, so we take two functions in the maximal domain of the operator, and basically it just means that they are locally absolutely continuous with absolutely continuous derivative, and then this will be true. I mean, it's not always true, but if it's true, then the operator has the strong limit point property. Okay, so one can put a more general operator there. In fact, it doesn't even have to be an operator. So the answer to that question is yes, but maybe you also regret asking that question because it actually gets a bit very general. But okay, let's look at that. So this is a very general way of looking at this. So instead of an operator, we can look at a closed linear relation, which is just a closed subspace of the direct product of the Hilbert space with itself. Now that would come, for example, from an operator if we take just the graph of an operator. So the graph, of course, will be F Tf, where F is in the domain of T, right? Then this is all these pairs form the graph of the operator, which is clearly a subset of the of H plus H. If it's a closed operator, then this is a closed subspace. But we can just take this subspace as an object in its own right, and then we don't even need to require that it stems from an operator. So in particular, we don't need to assume that for each f there is a unique Tf. Right, and then one can define the adjoint just by doing the usual thing, but in the language of this graph. And one can also define deficiency subspaces if one has a closed symmetric relation. So a symmetric relation is one which is extended by its adjoint. Right? So the relation is a subspace of the adjoint space. And now if we have a closed symmetric relation, then we can look at the adjoint, so this larger one, and we take for each lambda, which is not real, we can look at this. So this is basically an eigenvalue equation, but where we didn't write TF here, but just the second element of the relation appears on the left-hand side. And the solutions of this equation form the deficiency subspace. And one gets back the usual deficiency subspace for an operator if one just projects this onto the first element. Right? So in general, this space n lambda will be just the space of f in the domain, of f in the Hilbert space, such that f and lambda f are in the adjoint relation. Right, so and then if the adjoint relation actually comes from an adjoint operator, you can write it as the kernel of the operator minus lambda. Moreover, one can show that as usual, the deficiency indices, meaning the dimensions of these subspaces of the domain, are constant in the upper and in the lower half plane. So there are two indices, one for the upper half plane, one for the lower half plane, which gives the constant dimension of this. Okay, and then these can be used to construct extensions of the symmetric relation from restrictions of the adjoint. And for that purpose, one constructs a so-called boundary triple. So if you take a closed linear relation with a symmetric adjoint, so okay, now I swapped the notation a bit. This T is now the bigger one, right? So this is the big relation which comes into being as the adjoint of a symmetric one, or in other words, it has a symmetric adjoint, which would be the closure of the, well, it was closed anyway, so it's symmetric. Okay, and then what we do is we take another Hilbert space, which will be the space of boundary values, and mappings from the relation into this boundary space, two mappings, gamma naught and gamma 1. And then k, gamma naught, gamma 1 form a boundary triple if we have a generalized Green's identity, which is basically just integration by parts, but on a very formal abstract level. So we can basically move the hat basically means that we apply the operator, we can move that to the other side. So we integrate by parts, and we get these boundary terms. Moreover, one assumes that together these boundary maps form a surjective map. This is just to make sure that the boundary space is not too big. Otherwise, you could put a very big boundary space, which is not actually realized by functions in the relation. All right, so one has this. Now, once one has a boundary triple, one in fact also has a generalized Weil-Titchmarsh M function, which can be constructed in this way, that well, one needs to show that gamma naught restricted to the deficiency space is for a fixed non-real lambda is in fact a bijection between that space and the boundary value space. So we can look at its inverse, and then we compose the inverse with the other boundary mapping, and so we get a mapping from the boundary space into itself. That is the Weil-Titchmarsh M function. Now, if you look at it in another way, for example, if gamma naught is a Dirichlet trace, and gamma 1 is a Neumann trace, so you look at basically, well, the normal derivatives. If you think of an partial differential operator, for example, or an ordinary differential operator, then this is just a Dirichlet-Neumann map, right? So you look at those solutions, functions in the deficiency space, which have the given Dirichlet boundary data, and then you look at their Neumann boundary data. So it's just a general framework for seeing these things. And then once we have all that, we can also construct a Dirichlet form, which is of course what we will need for our help inequality on the left-hand side. One just takes this product here, f hat with g, and then one adds a certain boundary term. And because we have the this Green's identity, it is easy to see that this is in fact a symmetric relation. So if you swap these two, you get the same. And this is well, it's just because we move this bit here onto the left-hand side and this over to the right, and then you see that you get a symmetric expression. Okay, so that's a setup for a rather general closed linear relation. And now the funny thing is, for such a relation, one does have a help inequality. So this is a result of Matthias Langer a few years ago. So if you take a closed linear relation with a symmetric adjoint, then the following two statements are equivalent. The first thing is the help inequality. So the Dirichlet form can be estimated by a constant times the product of the norms of the f and, well, tf if we have an operator, for all pairs in the relation. And this is equivalent to the following condition, which is the generalization of basically Everett's condition for the usual Weil-Titchmarsh M function. And this is this condition here. So there should be a cone in the upper half plane such that this expression is positive. Right, so lambda is in the upper half plane, is 0. And so basically what we want is a certain angle theta. So this is theta, and this is again theta. So we have a symmetric cone around the positive imaginary axis, such that this particular combination minus lambda squared times m lambda has a non-negative imaginary part. So in here. And now that such a cone exists is maybe, well, okay, it has a chance of existing, because if you look along the imaginary axis, if you take lambda to be purely imaginary, then lambda squared is negative, so minus lambda squared is positive, and the m function, well, if you think of the standard Weil-Titchmarsh m function, in the upper half plane it has a positive imaginary part. So at least on this line here, this is already positive. So the question is only, can we open up a cone such that it remains positive in this whole cone? And then we make this cone as big as possible, and so we make this theta, in other words, as small as possible, and then the best possible constant for the equation can be calculated as 1 over the cosine of theta. And then also equality can be characterized by in terms of these boundary mappings, or of course, I mean, these are the trivial cases. If f or t, if one of these is 0, then of course we get equality. But there's also a non-trivial equation where we need to take well, extreme argument of lambda means that we need to have a lambda such that if we increase this cone a bit, then this stops to be true. Right, so basically here we must have positive sign, here negative sign. So lambda must be extreme. Then we get we can find inequality. Okay. Now, of course, this is a rather general theorem. If we have a relation which comes from an operator, then one can simplify this just on a technical level, because clearly the elements of the relation are then determined by elements of the domain of T. Moreover, if we are in the particularly happy case that the boundary space is one-dimensional, so there are only numerical boundary values, then it is sufficient to check this condition locally at 0 and at infinity. Now that has topological reasons. If you right, if we have the situation that we have such a cone at 0, and well, here's infinity. Think of a Riemann sphere here, right? So this is the North Pole here. So if you have such a cone here and here, So here the function is positive, here it is positive. We also know that it's positive on this imaginary axis. Well, there must be a connection. It can't be that this suddenly closes because this is a continuous function. Right? So if it were continuous and still we wouldn't find some, I mean, it can still become very narrow here, but the bottleneck can never shrink to 0, otherwise we would get a 0 on the imaginary axis, which we can't have. So it is sufficient to look at this locally, and then we have also criteria here. So at infinity, we only need to check the asymptotic of the m function if it behaves like c lambda to the alpha, and especially, well, it shouldn't be asymptotically constant, then we are fine. And at 0, we have the sufficient condition that if the boundary value of the m function is non-real or 0, then we have an equation, otherwise we don't. Okay, so that's the general setup. Now we want to apply this to, well, a tree, to a Laplace operator on a tree or a Schrödinger operator on a tree. Now, what do I mean by a tree here? Well, in some sense, it should be infinite to make this whole thing worthwhile. So we start from a root. Well, let's call it 0. And then it starts branching. And now we're interested in the case where this tree never stops branching. Right? So if, of course, one could have just some infinite leads, but this would not be so interesting. The interesting situation is the one where the tree just keeps branching all the time. So this is what we should think of. And right, then, well, if one has such a tree, then we can take a distance from the origin and take a tree. Well, take those elements which have a which have a distance less than r from the origin, and call that gamma r. Then the tree Laplacian arises from this quadratic form just by integration by parts. So here we have the minus the tree Laplacian f, and then we get boundary terms at 0 and where we have cut off the tree. Now if we assume these Kirchhoff conditions, then we don't get any contributions from the junctions inside, and that is very convenient. So we have only these boundary terms to worry about. Now, for our purposes, basically, we don't want to see these things. So we want that this goes away as we explore the whole tree. We can't do much about this condition at 0, but then if you think back to the original help inequality, at the point A, we didn't impose any boundary conditions. So this shouldn't be a problem, but we want to get rid of those. Now, fortunately, if we assume that the tree has infinite length, meaning that every path through the tree can be extended indefinitely, then we do have a strong limit point property. Now, let me just quickly mention, before we look at the proof of this, let me just quickly mention one curiosity here, and this is that maybe infinite length is not the right condition for this, even though, well, this is how we can prove it. Now, there's some indication that maybe this is not quite the right thing to assume here, because if you think of the special case of a radial tree, which is one where all the branches of a given generation are the same. So we have the first one, then we have. So the length of the branches are the same in each generation. Also, the branching numbers are the same. Then one can look at symmetric functions on this tree. So a function which only depends on the distance from the root, right, which is the same at corresponding points. And so we can map this into an interval from 0 to L, where L is the length of the tree. And so a symmetric function will correspond basically to a function which is on L2, 0L. But in order to make this an isometry, we need to take into account the multiplicity of these trees. Right? Here, of course, we have 2 of those branches. Here we have 6 of those. And so we get a weighted L2 space. Right? And then the tree Laplace turns into just this well, usual one-dimensional Laplace, but we get some rather inconvenient conditions because this function u will be continuous, but because of the Kirchhoff conditions, the derivatives at each of these points, which correspond to a junction, at these points, there will be a jump in the derivative, which reflects the fact that now we have some dissipation into several branches. And so this is a bit inconvenient to look at, but one can fix it by a trick, right? So if we have some function here, okay, like this, and now its derivative would suddenly be only 1/2 of the original one. Now we can fix this by squeezing this interval to half the length and keeping the corresponding values of the function. Then we get also a continuous derivative. If we do this for all the intervals, then we get, so this is just this construction, then we get a function v which is continuous with a continuous derivative on an interval 0, b. Right, b is a bit shorter than L because I shortened all these intervals corresponding to the multiplicities. And but then, so we get a stronger weight here, but we get for the tree Laplacian now just such a simple Sturm-Liouville equation without any extra jump conditions and with a weight which fits the weight of the space. This is an isometry again. And so we can just apply the usual Sturm-Liouville theory, and we get that, well, it's easy to see that this is the limit point case at infinity if and only if the integral of the weight is infinite. And then it's also a strong limit point case, as one can show. But now if one calculates this integral, the integral of the weight, it is in fact just the volume of the tree. So it seems that the correct condition for limit point case at infinity should be not infinite length, but infinite volume. Well, but I mean, this is only for the symmetric part on a radial tree, and for a general tree, we have only this theorem. But it would be interesting to know what happens for a finite length, infinite volume tree. Okay, now the proof of this theorem is all based on staring at this calculation, which we've already seen. Right? It's just integration by parts on the part tree. Of course, we want to send r to infinity to exhaust the whole tree. Now, if we do that, you see immediately on the left-hand side, this is increasing in r. So it either converges to a finite limit or it goes off to infinity. Now, if it went off to infinity, then, this is just a constant. This is bounded by Hölder because we assume that f and f double dash are in L2. So this is bounded. So if this goes off to infinity, this must go to infinity. And in particular, this goes off to a positive real infinity. So if you take the real part, we see that the real part of this must go to infinity. Right, here it is. But now this is really just the derivative of the sum over all the cutoff points, these points here where we're cutting, where it's bleeding, as it were. The derivative of f squared taken over these, summed over these points. But then if the derivative tends to infinity, then clearly this itself must tend to infinity. So if we integrate it, it must tend to infinity, but that gives us the L2 norm of f, which was finite. So we got a contradiction. So this can't go off to infinity, so it's finite. So it converges to a limit. This converges to a limit by Hölder. This is constant. So this tends to a limit. All right, so this limit exists. And now again, the same calculation as before. The real part of that is this. And now because it converges to a limit, if this limit were positive or negative, then this would be, I mean, without the derivative, this would be linearly growing at infinity, so it would still not be square integrable. Therefore, again, by square integrability, this limit must be 0. So the real part of this middle term tends to 0. Right? Now the imaginary part will also tend to 0, and in order to see this, we play a bit with the operator. So if we take now the minimal operator for the tree Laplacian. Its adjoint domain is the domain D, which we were talking about, and the now if we can make this into a nice self-adjoint operator by imposing a Dirichlet boundary condition at 0, because if we do that and we take a function f, which is a solution of this eigenvalue equation, then again the previous calculation, only instead of minus f double dash I have a plus minus if here. Now the left hand side is clearly real. This is purely imaginary. This, as we have seen, is also purely imaginary because the real part vanishes. So this is real, this is imaginary, so they both must be 0, and therefore we see that only f equal to 0 solves this equation, which makes A a self-adjoint operator. And then again, by an integration by parts, if you look at the imaginary part of this, we can write it as, well, the form again. And here we have now the self-adjoint operator. Now, because it's a self-adjoint operator, we can move it back and forth. So this is real. This is also real, so the imaginary part is 0. And so the imaginary part of that is also 0. And now this is true for all f in the domain of A. But now this differed from the domain D of the maximal operator only by a boundary condition at 0. But if we are looking at the behavior at infinity, we don't know anything about the boundary condition at 0. So this is in fact also true for all f in the maximal domain. And then we get the theorem just by the usual polarization trick. So we replace f with f plus g and f plus ig, and then we get this. Okay, so this shows the strong limit point property for the tree. And okay, now if we take a tree of infinite length, now we can also add, for example, bounded potential, so we don't get any problems with the domain. It's still the same domain. And we take now these boundary operators, the Neumann boundary operator and minus the Dirichlet operator. Then one can check that these form a boundary triple for T, with the boundary space just being the set of complex numbers. So we are in the good situation where we have a one-dimensional boundary space. Then the Dirichlet form, no big surprise, is just what one would expect. Right, and the deficiency subspaces can be they're one-dimensional. We've seen that here because with this one-dimensional restriction, we got a trivial space, so the deficiency subspace is one-dimensional. And so we can look at this Weil solution here, which satisfies, for example, this condition that the derivative at 0 should be 1. And then the m function is just given by minus the value. So the m function in this case is a Neumann to Dirichlet map, or minus a Neumann to Dirichlet map. All right, and then we just plug this into the general theorem, and we get this help inequality for a metric tree. And with characterization of the best possible constant, again in terms of this criterion here. And m is just a complex valued function now, which is an analog of the usual Weil-Titchmarsh m function. Okay, now we calculated an example here. Now this is again a very special tree. It's like the one which I mentioned here, even though it's not even simpler. It's not only radial, but also all the lengths of the branches are the same, and all the branching numbers are the same. In this case, one is very much in a situation similar to a periodic one-dimensional problem. This Weil solution, which we have, so the L2 solution for a non-real lambda, is a symmetric function under swapping these branches. This is just because we have deficiency index 1. It's a one-dimensional space. If we swap branches, we would get another L2 solution, but it must be linearly dependent on the first one, so it's easy to check that they must be the same. And also because of this fact that for a symmetric function, whenever we have a branch into B sub-branches, then of course we lose, the derivative splits into 1 over B parts because of the Kirchhoff condition. And so we get some property.
Branching point, the derivative. Now, if you take this into account, we can set up something like a Fouquet theory, for this problem. So we start from the n minus first branching point, just to the right of it. Then we propagate along the branch by using the canonical fundamental system on an edge. So this is a fixed matrix psi of L, which brings us just to the left side of the next branch, and then at the branching the function is continuous, the derivative gets a 1 over b, and so we get in total such a transfer matrix from one step to the next. And now, like in Floquet theory, it is just a matter of looking at the properties of this matrix to get information about the asymptotics of solutions. So now if we think again of this Weil solution, psi lambda, again, because we have the efficiency index 1, it must be an eigenfunction of the of this matrix A. And that is because this tree, it's not only symmetric under swapping branches, but it's also self-similar. Right? Every subtree is again the same as the original tree, and therefore, if you go to right, if you look at the psi on the whole tree, and then we'll just look at this part of it, it must be linearly dependent on the original psi, because it's only a one-dimensional space which gives L2 solutions, and so the function here must be a multiple of the function there, and so we get this eigenvalue property. So mu must be an eigenvalue of A, and the eigenvector will be the psi at 0, so minus lambda over 1, and okay, now I'm running out of time, but well, it's just a standard Floquet theory with the only difference that in the standard theory the determinant is 1. In this case it's 1 over b. So one needs to look at the eigenvalues will have a product 1 over b. So one of them will be, generally speaking, bigger than 1 over square root of b, and the other one smaller than 1 over square root of b. And only the one which where this is less than 1 over square root of b will give an L2 solution. So in particular for the psi lambda, this mu of lambda must be smaller than 1 over square root of b. Okay, and now here I've just written again the eigenvalue equation. So this is the matrix A. This is the eigenvector there. Yeah, this is the mu of lambda, and this gives us a way of calculating the m function just from the first line here. All right, you see this is well, you multiply and calculate mu of lambda is just psi of L over theta of L minus mu of lambda. We know that mu of lambda is pretty small. Now it's just a matter of looking at what psi and phi, the solutions of the canonical fundamental system, do as lambda moves around in the plane. Now, if we look at infinity, right, at infinity we need to have some nice behavior of the m function, but well, one can work out the asymptotics as lambda tends to infinity as the imaginary part of lambda tends to infinity, well, this is the asymptotics for the theta and the phi. The mu of lambda is bounded, and these are actually growing exponentially, so one can easily check that m of lambda is this. So we get a behavior like 1 over square root of lambda, so it is not asymptotically constant, and the condition for the help inequality is satisfied. Now at 0, we need to look at the okay, we need to look at the quasi-discriminant, which is the trace of our transfer matrix A, and so for the usual Floquet theory, the critical number is 2. Here it's 2 over the square root of b. If this number is less than that, then we get non-real eigenvalues, complex conjugates of this size, quasi-stability. Otherwise, we have quasi-instability. And well, the upshot is that we need to have quasi-stability. If 0 is in the quasi-stability band, or 0 is Dirichlet eigenvalue, then the m function has the correct behavior at 0, and so this behavior at 0 here, and therefore we will have an equality. We also did some numerics. One can actually follow this program and calculate the optimal constant numerically. So here you see the, well, this is this imaginary part. Well, it's actually the negative of that. This one here, I didn't put the minus, so it's, we need to look at where this is negative. So this is the good range. Right? This is, here's the angle from 0 to pi. And this is, you see in this middle region, we are fine. And so in order to see how big we can make the angle, one needs to look at the zeros of this. This is actually not important because this is closer to pi half. And then if one calculates that zero as a function of the distance of lambda from the origin, then we got something like this. Now this is this seems to be an artifact of the calculation, so better numerics actually gives something going up like that. And now in this particular case, for this, this is a Airy type equation. This just approaches the asymptotic limit of pi over 3, which gives a help constant of 4. Okay, yeah, my time is up. So this is a paper where you can find these results. Thank you very much.
Comments? Question? Yes, please.
Actually, one question. Can you? I think you might be able to replace on this way to treat the edge by some decoration and use the same one on the generation. Did you consider such cases, or
You replace it by what?
so you replace an edge by a sort of subgraph which having two ends, like for example you put a ring.
Ah, yes, yeah. So if one looks at the at this theorem here, that one. For the strong limit point. In fact, here we didn't use that it is a tree. This actually works for graphs. What we only need is that it has only one free end and is infinite in all other directions. But yes, you could have some loops also inside. Well, for the other, now for the health inequality, we didn't look at that. It might be that we're using, well, I mean, in this business with the y function, of course, we're looking at specific properties of the solution. It might be that there is some.
Other questions? Well, if not, thank you very much.